All right, you guys, today we are going to start out talking about vectors and coordinate systems. So I've got two vectors here and a coordinate system. Our coordinate system is showing us north, south, east, and west. And we're going to treat this just like we would in our math class, where north and east are going to be positive and south and west will be negative values. Now let's talk about maybe we're going on a hike, all right? We're going to start over here. And we're gonna hike, and we've gone east for, let's say, 4 miles. And then once we've gone east for 4 miles, we're gonna head north for 3 miles. But what I want is I just want displacement. This would be a distance traveled. We would just do 4 plus 3, and we would get that we had traveled 7 miles. But I don't want that. What I want is I want to know how far was from start to finish. I'm concerned with this vector right here. All right? What that vector is called is the net displacement. All right, that's going to be our net displacement. And if I want to find that net displacement, I'm going to use some letters that are familiar to us when we're talking about triangles. So let's say that this 4 miles is vector A, and this 3 miles is vector B, and what we're trying to solve for here is vector C. So if we have vectors A and B and we want vector C, what we're going to do is that vector C is equal to vector A plus vector B. So this vector C here will be equal to vector A plus vector B. And the sum of these two vectors is going to be called our resultant vector. So this net displacement is our resultant vector. Okay? And you'll notice the figure we drew here is a shape we like. This is a right triangle. So to find the magnitude of C, we can use the Pythagorean theorem, can't we? Because whenever we want to find the hypotenuse and we're given two sides, that's what we like to use, which is C squared equals A squared plus B squared, which would mean that C would be equal to the square root of A squared plus B squared. And here, you'll see we don't have the little arrows over it because we're just dealing with magnitude, okay? And if we're just dealing with the magnitude and we want to find this hypotenuse, we're going to have that C is equal to the square root of our A, which is 4 squared, plus our B, which is 3 squared. Now, if you guys take a second to solve for this hypotenuse and you do the square root of 4 squared plus 3 squared, you should get that C is equal to 5, which here, these are in miles, so C would be equal to 5 miles. So our magnitude of vector C, our net displacement would be 5 miles. Now that only gives us a magnitude. There's no direction with it. Here we went 4 miles east and we went 3 miles north. I want a direction with my 5 miles. So the next thing you might be wondering is, well, how do I find the direction with my 5 miles? Well, once again, we can easily find this direction or angle with a method that we previously used. If you guys remember correctly, the tangent of an angle, of angle theta, is going to be equal to B over A. Because SOHCAHTOA, so our opposite over our adjacent, gives us this angle, which is the angle that we want to find out the direction of our 5 mile magnitude. So if we do that, we'll get that theta is equal to the inverse tangent of b over a, with b being 3 and a being 4. So we're going to take the inverse tangent of 3 over 4, which should give us an angle of 37 degrees. So now we have our magnitude of 5 miles. We have a direction of 37 degrees. However, this is 37 degrees north of east, all right? So 37 degrees northeast, which means vector C overall is going to be equal to 5 miles, 37 degrees northeast. Okay? So the word vector may sound scary, but all it means is that you're basically finding a hypotenuse of a triangle as well as its angle. Now, does it get more complicated? Yes, but this is what we're going to start off talking about, okay? Now, remember the difference, though, real quick, just between a scalar and a vector, is that if we were asked for the scalar, we would have stopped at 5 miles because that's just the magnitude. The vector is that magnitude and the direction. So that's why we had to take it a step further and find that angle. So let's move on to another example sort of with this to help us out some. All right, since you sort of just got thrown into an example as soon as we started class today, let's sort of look at a problem and talk through it together now, all right? So if we use graphical addition to find displacement, that's the same way to say the thing we just did. We used graphical addition to find displacement. So let's talk about a bird out flying. The bird's going to fly 100 meters due east from a tree. So 100 meters due east. Then they're going to fly 50 meters northwest, which is a 45-degree angle north of west. So we're going to have them go 50 meters, 45 degrees northwest. And what we want is the bird's net displacement. So we are looking for from start to finish. We just want this net displacement because this is where our bird started. This is where our bird finished. And we're concerned with that right there. So if we're looking at our vectors, we would have that vector A is 100 meters east, and then that vector B is 50 meters, 45 degrees northwest. Now, something that I do want to note really quick is you'll notice that I'm putting these little areas over this. That's because it's vector A and vector B. If we leave out those arrows from here on out on a vector, we're just considering it magnitude. So remember what our vectors are. We have displacement as a vector, velocity is a vector, acceleration is a vector. So far, since we hadn't learned about vectors yet, you just got to write the letter. But now you're going to want to make sure to put a vector symbol over them because now you know what they are and how to represent it. Okay, what we're faced with now, though, is we want to find this, and this is our C, right? We want to find that net displacement. This is not a right triangle, though. Do you guys remember what laws we're going to want to use if we have something that's not a right triangle? Well, I'll give you a hint. You've probably heard about it, the law of cosines. So our law of cosines is going to let us know that C squared equals A squared plus B squared minus 2AB cosine of theta. All right, that is our law of cosines. And right now, this is that theta that we were provided with. So when we look at this, if we just want C, that means that C is equal to the square root of all of that. So let's go ahead and plug it in. Our A, as you notice, these are just magnitudes because there's no vector over them. It'd be 100 squared plus 50 squared minus 2 times 100 times 50 cosine of 45. Okay, when we type that in, we get that C is equal to 73.68 meters. So that's our magnitude of C. Now we need to find this angle, which we're going to call phi. So we want to find phi because phi is going to give us the angle at which this vector is going. So once again, we can use our law of cosines. Here it tells us that b squared is equal to a squared plus c squared minus 2ac cosine of phi. And what we're solving for is phi. So if we solve for phi, we are going to want to start by subtracting over b squared and adding over that 2ac cosine phi so that it's by itself on one side. So we're going to get 2ac cosine phi equals a squared plus c squared minus b squared. Next, we can divide both sides by 2ac. And we would divide both sides by 2ac. That gets rid of the 2ac over here, which means that the last thing we have to do is take the inverse cosine of all of this. And we'll end up with phi equals the inverse cosine of a squared plus c squared minus b squared over 2ac. Which means that our final step is we get to plug all of that in. So it's going to be inverse cosine. Our a squared, once again, you'll see these are magnitudes. It's going to be 100 squared plus our magnitude for c that we just found of 73.68 squared minus b squared, which we were given as 50, divided by 2 times a, which was 100, c, which is that 73.68. So we have inverse cosine of 100 squared plus 73.68 squared minus 50 squared divided by 2 times 100 times 73.68. When you type that in, you should get that phi is equal to 28.67 degrees. So now we have a magnitude and we have a direction, which means we can write out what our vector c is. The final answer would be that vector c is equal to 73.68 meters, 28.67 degrees north of east. So that's going to be northeast. And that gives us what our net displacement is for our bird who flew 100 meters east and then 50 meters 45 degrees north of west. If you guys have not learned the law of cosines yet, please let me know when you get to class because I need to know if I'm assuming too much there, all right? To further talk about vector addition, sometimes you'll get asked to add together maybe two vectors like this. Now, these vectors are known as having a tip and a tail. The tip is going to be the direction the arrow points in. The tail is going to be the part that doesn't have an arrow on it. One of the main ways that we like to add vectors in physics is called the tip-to-tail method. With that tip-to-tail method, what we can do is, let's say we have vectors D and E here. We can take vector E and we can move it so that it is now tip-to-tail with vector D. So it's going to be the same magnitude and the same direction. It's just now over here so that they're tip to tail. What that does is it makes it so when we're finding our resultant vector, F is just equal to E plus D. And it's like the examples that we have already looked at. The other rule that you can use, if you're more comfortable with it, is the parallelogram rule. What the parallelogram rule is if we get this back to its original condition, where we just had E and D, it would be like we would complete the parallelogram, which would let us know that our resultant vector of F would be right there, and it's still going to be equal to E plus D. But it's a different way to see it than the tip-to-tail method, and that's considered the parallelogram rule. Now, that's pretty simple though, right? We've just got an E vector, a D vector, we're trying to find an F vector. But what happens if things get extra funky? Sit back in your seat, wait to see what I'm about to draw. Okay, so what if we have something like this, where we're traveling here for our D1 vector, then we come up here, that's going to be our displacement 2, then 3, distance 3, and then 4 brings us here. So our start is over here, and then we end or finish over here. And we're asked to find that net displacement. Well, if we're asked to find that net displacement, luckily, it's still just going to be drawing from start to finish. And that would be our net displacement. However, the question becomes, how do we find that? Well, just like with all other addition, our vector D net would just be equal to D1 plus D2 plus D3 plus D4. Okay? So you'll see that these are all vectors, which means that once again, you're going to need to use their magnitude and their direction in order to find the magnitude and the direction of our ending displacement. Don't worry, you don't have one this crazy to work on yet, okay? But let's maybe look at some more vector math for a second. So to start out, we don't just add vectors. We can add vectors, we can subtract vectors, we can even multiply vectors. So let's look at vector A right here. Vector A is made up of magnitude A and a direction of theta. Well, what if we wanted to multiply A times something? What would happen then is this new piece that we have, maybe we're going to call this vector B. Vector B would be equal to some constant times A theta. So when we multiply a vector, all that's really going to change is its magnitude. Its direction gets to stay the same. Well, what if we wanted to multiply by a negative number though? Okay, so let's say this is a positive constant and we have A again. But now we want to multiply maybe by negative 2. So if we multiply by negative 2, now we would have a negative 2 A vector. And what that does is it expands the magnitude by 2, and now the direction is going to be opposite. So the entire vector's direction is going to be opposite, and its magnitude would be increased by 2. We just wanted to maybe multiply A by negative 1. Well, if we just multiplied a by -1, it's going to be exactly equal in magnitude, but just opposite in direction. So if you multiply by a negative, now your vector is equal in magnitude, but opposite in its direction. What if we had vector A and vector C, and we were curious about what is vector A minus vector C? Well, if you want it to be in something that you're familiar with, it's actually just A plus a negative of your vector C. So it would be like A plus our negative of vector C, which would be in the other direction, equal in magnitude, opposite in direction. Now, when we do that and we're solving for it, we have two options. Once again, we can either do the tip to tail or we can do the parallelogram. Now, if we did tip to tail, what would happen is we would want to take this negative C and we would want to move it up here so that it would be tip to tail. And our resultant vector would then be from tip to tail here. This would be our A plus negative C. If we were to go the parallelogram route again, we would have A and our negative C, and we would once again want to complete our parallelogram to then solve for our A plus negative C again. Now let's look at an example with velocity and displacement. Carolyn is driving her car north at 30 kilometers per hour for 1 hour, and then east at 60 kilometers per hour for 2 hours, then north at 50 kilometers per hour for 1 hour. And we want her total net displacement. So we know that velocity, which remember we just is a vector, so now we need to be sure to include that it is a vector, is equal to displacement, which is also a vector, over change in time. Time is not a vector. So if we want net displacement, we can rearrange this equation to get that our displacement is equal to our velocity times our change in time. And you'll notice that with Carolyn, we're given her velocity and we're given her time. So for her very first displacement, we're given that she is going 30 kilometers per hour north, and she's continuing on in that direction for a time of 1 hour, which means that her displacement during that time is going to be 30 kilometers north. Next, we have that she is going 60 kilometers per hour east for 2 hours. So 60 kilometers per hour east for 2 hours. That's going to give us a displacement of 120 kilometers east. Finally, we have her third displacement, which we're told that she's going 50 kilometers an hour north for 1 hour. So we would do 50 kilometers per hour north times 1 hour, which lets us know that her displacement during that period of time was 50 kilometers north. Now, if we want to find her net displacement like we're asked for, we're going to have that our net displacement is going to be equal to the sum of all of her individual displacements. All right? Now, when we do that, it's really going to help us out if we actually draw a picture. So over to the side, I'm going to write down each of my displacements that we just found so we can refer back to them during this picture. All right, so if we're drawing what Carolyn does, we are going to start by going 30 kilometers north, 120 kilometers east, and then 50 more kilometers north. So here's 30, 120, and 50. This is where she started, and this is where she ended. We want her net displacement. So we just want to know from start to end, how far did Carolyn go? Okay. Now, we can look at this like a right triangle, thankfully, okay? So when we do that, we can sort of use, this is going to be our theta, and here we have a right triangle, right? Now, we know that the length here is 120 kilometers. Then to find this one, we would do 30 plus 50, which is going to give us 80 kilometers. Now, if we want to find the hypotenuse of this right triangle, we're going to use the Pythagorean theorem. So I'm going to end up with C equals the square root of 120 squared plus 80 squared. If you do that, you get that it is equal to 144 kilometers. So that would be the magnitude of her displacement. And then just like with that first example we did, we can find this theta by doing the inverse tangent. So we are going to have the inverse tangent of 80 over 120. And if you do the inverse tangent of 80 over 120, you get 34 degrees. So by finding the magnitude and the direction, we can say that Carolyn's net displacement is equal to 144 kilometers at 34 degrees northeast. So 144 kilometers, 34 degrees north of east.